Hello and welcome to our demonstration of the BI4ALL data models. My name is Peter Nolan and I'm the founder of Instant Business Intelligence. During this presentation I'm going to take you through the following agenda. We'll talk about some names you should know, some key issues in data modeling, some traditional data warehouse design mechanisms such as star schema and time variance plus stability analysis, which has evolved into Data Vault, business intelligence modeling best practices, and then we'll get into the BI4ALL data model. We'll talk about the terminology of it, the naming standards, we'll talk about each type of table, we'll go through some details of BI4ALL, and we'll go through a live demonstration of the data models. Now obviously, given that we're talking about data models, and we're going to be talking about data models for the next hour or so, if you're listening to this, you should understand dimensional data modeling. If you don't understand dimensional data modeling, then this presentation will well go over your head. So this is not a presentation which is a general presentation for the general population. This is a presentation of the information that we are able to make public about BI4ALL for those people who've got an hour to spend to look into BI4ALL as a data model. Of course, the two big names within business intelligence are Bill Inman and Ralph Kimball, who I know both quite well. And Bill Inman is typically nominated as the father of data warehousing. Bill has been a prolific writer over the years, and I met Bill in, I think it was September 1993. He was the public pioneer of data warehousing, and as always, pioneers have arrows in their back. So Bill has had his fair share of detractors over the years, which I think is very ungrateful and ungracious of those detractors. He was the originator of the idea of the time variant plus stability analysis data models, and that was a very brilliant idea, given that he came out with it in the late 80s. And Bill came from a system analysis, data modeling, enterprise architecture background. And that is a very different background to the background Ralph came out of. So all the work that Bill has done over the years has been very focused around architectures. And what Bill has done is give architects a set of tools and rules and ideas that the architect then had to go through and understand and select for himself or herself. A great deal of people have come to me over the years and talked about how Bill Inman defines this rule and Bill Inman defines that rule. And my response to that has always been rubbish. I know Bill, and he doesn't define rules. He gives you his best ideas, and it's up to you to be smart enough to figure out how to use them. And I've said that to Bill on a number of occasions, and he said, yes, that's exactly what I'm doing. He's trying to give people ideas about what can be done, and he has tried to start software companies, and he's made products and things like that that have gone on to be successful. But mostly Bill is about architecture, and if you sit back and think about what he's telling you, you will understand that's what he's on about. Ralph Kimball is also somebody who's made great contribution to me over my lifetime, and whom I have said thank you to in person for that. And Ralph worked at Xerox PARC, and he was a co-inventor of the Xerox Star workstation way back in the 70s. Ralph was the co-founder of a company called Metaphor Computer Systems, and that was the world's best DSS software until IBM killed it. And Metaphor lives on as a product called Meta 5. IBM really did not do Metaphor any favors by buying them and then trying to help Metaphor be, quote, successful. And if you stop and think about the work that Ralph did in the early days of Metaphor Computer Systems, they solved the problem of doing decision support systems on Motorola 68020 processors with 16 megabytes of memory and 320 megabyte disk drives. And the key innovation that Metaphor was able to come up with was the idea of implementing a dimensional model on a relational database management system. So Metaphor Computer Systems actually built their own relational database manager and built star schemas on that relational database manager, because at the time, 1984, there were no relational database managers around for them to build this solution on. So the dimensional model on a relational database was Ralph's baby, and this was done because there were other products which used multi-dimensional databases at the time, most notably IRI Express, and Metaphor Computer Systems were going to go head-to-head in competition with IRI Express. Now, vastly different to Bill, Ralph came from an engineering background, and all that implies. So Ralph is very much an engineer. He looks at things in an engineering type of way. He looks at defining fairly definite rules for how things should be done, as engineers would do. And so those people who still go on about the Bill versus Ralph thing are very, for me, very tedious people. I've talked to these guys in the early 90s, and there was no particular competition between them. They were both presenting ideas, and you could take their ideas or leave their ideas as you would wish. And we'll see in the course of this presentation that combining their ideas was actually the best way to go. The key issues in data modeling are ease of use for the end user, if the model is easy to use, and what has been done in recent years is that a lot of models are hidden behind universes and catalogs and things like that. Speed of response for the end user from the database is a big issue and continues to be an issue no matter how fast the machines get. Ease of extension or expansions for the IT developers, ease of understanding for the IT developers, the ability to store large amounts of history, and it's getting ridiculous now. If you'd have told me 15 years ago the size that data warehouses were going to get to, I would not have believed you 15 years ago. And the lowest cost of development and maintenance of the ETL to populate the models. The biggest single 5-year cost of ownership with owning a data warehouse is the development, maintenance, support of the ETL subsystem. And so anything that can be done about making the ETL subsystem easier to manage around the model is a good idea. Now that's 6 bullet points. Obviously there could be many more listed, but if you could hit all 6 of those bullet points fairly well, then you would be doing very well in your data modeling. Now there were, many years ago, 3 different design methods for business intelligence projects. And the choice of design method used depended on many factors. So before 1996, in my experience, people either chose star schemas or chose time variance plausibility analysis, and nobody chose to mix those two. And so in the early 90s, there was this sort of question about Inman versus Kimball, which way to go, because people went one way or the other. They didn't mix these two ideas. Now, star schemas were particularly well suited to transaction type problems. So if you were a telephone company or you were a bank, then star schema suited you. If you were a retailer or a fast-moving consumer goods manufacturer, these companies all revolved around transactions against a very small set of products. Average retailer didn't carry that many products in the early 90s. It's changed a little bit now. So star schemas were very well accepted in initially the retail area, and that was the area that Metaphor went after. And then things like telephone companies and banks and things like that moved with star schema style data warehouses. But there's another whole class of data for which star schemas were poor, and the best example of that is customer data and account data. So customer data or account data is not transaction based, and things in it tend to change over time merely by the passage of time, and not by the issuance of a transaction. And the best example of that is the age of a customer. So there was this information that existed within companies that was not really suited to this whole dimensional model scheme, and time variance plus stability analysis was a data modeling technique which said changes to non-transaction type data can be archived over time in this data modeling technique, and all the history of that data can be then stored to be requeried at a later point in time. And that was quite popular in the early 90s. And then of course there's the ever-present third normal form, and most operational data stores are implemented that way, most operational systems are implemented that way, but third normal form proved to be quite unattractive for a business intelligence system because of the cost of all the joins. Now, companies such as Teradata were very big into third normal form, or third normal form plus time variance plus stability analysis in the early 90s. So with these different modeling techniques, let's just talk about why they were used. Now, star schemas are inherently understandable by business people. They match the business model, and they are intuitively obvious when they are relatively simple, right? So star schemas had their rise and rise through companies like Metaphor and then Red Brick, and the books that Ralph Kimball wrote in the mid-90s, because people could come to grips with them. And I remember in 2000, when Microsoft first started talking about star schemas, I commented to a client that maybe it's time I got a new job, because star schemas were becoming so commonplace that even Microsoft was talking about them. Now, star schemas are also very easy to query. They support complex questions easily. You don't get wrong answers due to join problems, which you do with third normal form and time variant models. They give excellent performance on star schema-aware databases, like the old Informix, Oracle, DB2 style databases. And now things like Netezza and all the other appliance products are coming out. All the appliance products all support star schemas. What does it look like? Well, in the simplest of terms, there's a central table which has some kind of numbers in it, such as the amount or the cost or the number of transactions, and this is what is called a fact table. And most people listening to this presentation had better know this. Time dimension, demographic dimension tables, branch, for example, the transaction codes, and the account would constitute a star schema today that would be considered too trivial to be useful. Star schemas use integer keys, and why use integer keys? Because integers are the fastest data type to operate on. They are shorter than things like account numbers, and so they give you reduced space and throughput as well. And the speed from the disk to the processor is what's most important. And flexibility, integer keys and not embedding any intelligence into the keys allows such things as multi-level summary tables with no IT involvement to create new summaries, but that feature has been largely left alone in the last 10 years. Ralph and I stopped talking about multi-level summary tables many years ago because it seems people are just not interested in learning about these things. Most importantly, when you use integer keys, you can build very large stars. Now, even today, we see people making the mistake of building some form of intelligence into integer keys. And I made that mistake in 1993 and never made it again. So I'm not quite sure how 19 years later people are still making this mistake, despite the fact that people like me have told them it is. Now, time variance plus stability analysis was an entirely different idea, and this was why in the early 90s there was quite a little bit of confusion about the Ralph versus Bill thing, because what they were both talking about data warehouses, but they were talking about modelling techniques which were so vastly different that the average person couldn't understand it. And it was only when I was trained, I actually went to the Metaphor Users Conference in San Francisco in 1993 and met Bill. I'd never heard of him before then, and so I bought his books to find out what he had to say. And I was also trained by Metaphor on building dimensional models. It was only when I read Bill's books and I learned how to build dimensional models that I realized that these two things were vastly different creatures intended for vastly different purposes. You know? So why use time variance plus stability analysis? Well, if you want, I want to be able to see the value of any field at any time in the past in any of the data I had. Then you are going to build a time variant plus stability analysis model, or today that would be called a data vault model. These databases were archival databases, and they were required to be built when people really didn't know what they wanted. Okay, so if you did not know what information you needed to store about your business in order to more effectively manage it, then a time variant plus stability analysis model was definitely the way to go. Now, these had a very specific, very popular implementation, and that was life insurance companies. If you were a life insurance company, the idea of a time variant plus stability analysis data model was absolutely what you wanted. You wanted to understand all the changes in the characteristics of all your clients and all their financial positions over a very long time frame to properly price your life insurance policies, right? That's what life insurance policies were all about. None of this, we're doing so many transactions per day and making so many sales per day idea. Life insurance policies were about, we're taking the risk on this person dying, and we need to understand what that risk is. And so this kind of database really found a very happy home in life insurance. And I spent a large portion of my early BI career in life insurance, and so I understand this quite well. And indeed, the very first project that I did, the requirements definition from the Director of Marketing was, I want to be able to answer any question that I come up with. I don't know what that question's going to be, and I want to get the answer before I forgot why I asked the question in the first place. Now, in 1991, as an IT person, that did not form a very good requirements definition for me. And needless to say, my first efforts at delivering on that requirements definition of, I want to ask questions, I don't know what they are, and I want the answer before I forgot why I asked it, did lead to something of a disaster in my very first project. And so building these kind of systems was not easy until we discovered time variance plus stability analysis. Now, these data models are not easy to query, and you can't give them to business people to query. And I recall in 1994 when I went to a seminar that Bill was out to Australia with, and he was going through this in detail. As I came to understand what he was talking about, I said to him, Bill, nobody can ask a question of this data model you're proposing. And Bill laughed and looked at me, and there was over 100 people in the room. Bill said, the appropriate query tool for this kind of data model is called a COBOL programmer. And that's how it was. You had to be a programmer to be able to understand these data models. What does it look like? If we take something like customer information or account information, we take that data and we split it in three. And we have the highly volatile data, the medium volatile data, and the low volatile data split in three. Now, if I'm a customer, what kind of data might be split? Well, the low volatile data will be things such as birth date and sex and city of birth or citizenship. This information changes very rarely. Medium volatility data might be something like your current financial position or your your credit score or something else like that, which might change on a roughly annual basis. And then the more volatile data might be your net value to a bank at a particular point in time, or your customer value index, which might be calculated monthly, or something like that. Now, if we were to think about a bank account, there are some things about a bank account that translate well. For example, a low volatile piece of information on a bank account is the opening branch. Okay, that doesn't change. The domicile branch is also a low volatile piece of information. It might only change once every few years. A medium volatile piece of information on a bank account would be something like the interest rate. The interest rate on a bank account changes maybe every 3-4 months, maybe 6 months. And so that is a piece of information that you'd want to store on the medium volatility. And on the high volatility table, you would store things like balance. The balance of a bank changes on every day or every couple of days, whereas the opening branch of a bank account never changes. So if we take this piece of data, such as a bank account or a customer record, and we split it into 3 pieces based on the volatility of the individual data elements that we're splitting, and we store the natural key and a date from date to, pretty soon you can see that if I take a snapshot of this file every night and I archive that which has changed every night, we build up over time an archive of all the values of all the fields for that piece of information. Now obviously this is expensive, or certainly it used to be expensive, to store every value of everything over a significant period of time. Now this was the equivalent of a type 2 dimension in the dimensional model, but the issue with type 2 dimensions was you tended to store everything within the dimension record, even if it wasn't changing. So this kind of stability analysis gave us a lower amount of disk space usage because the things that didn't change very often were stored down here, and the things that changed more often were stored here, and you didn't keep too many copies of stuff that wasn't changing. So that's what time variant plus stability analysis looked like. So the best practice since 1996 has been this. In 1996, a colleague and I discussed these modeling concepts for one of his customers, and it turned out that we decided that what we would do was, the ODS was added later, we would build an archive data model, third normal form time variant model at this level. Older detail would be archived in 3NF time variant model, and we would build dimensional models on top of this archival form. So what we basically did was take the best ideas of Bill and put them here, and take the best ideas of Ralph and put them here. Okay. Now the gentleman that I refer to was ex-Metaphor, and he was trained by Ralph, and he was a close personal friend of Ralph's. So he understood dimensional models very well. He didn't understand this stuff very well, whereas I understood this stuff very well, and at that time I was rather a novice at dimensional models. This other gentleman was indeed my mentor at the dimensional model side. And so we discussed and agreed that he would test out with his customer combining the two modeling techniques. Now this turned out to be a tremendous idea, because what happened was we were able to build different images of dimension tables out of this archive to plug into these dimensional models. So the primary problem with dimensional models, which was they didn't store all the data as an archive, was suddenly removed because of this archival layer. Now my friend worked at BI4ALL003 at the time, and this went on to become the standard design mechanism for BI4ALL003, and then the ODS was added in later, as a third normal form model, I think in about 97. And so this became best practice. And this was adopted by PricewaterhouseCoopers, IBM, and many other consulting firms as the best practice. And about 8 years later, Claudia Imhoff and some other people actually wrote a book about this, saying this was a good idea. Now, the issue with this was that the thickness of these lines is intended to convey the meaning of the complexity of the ETL processing in those lines. So it was a fairly difficult thing to build one of these. Now, the BI4ALL proposition says that this archival data store can be done in star schema. The older detail can be done in star schemas. These can be virtual data marts and just processed through views, and this becomes much easier to build. And my line has disappeared, it seems, in this particular slide. Getting from here to here is hard, but getting from there to there is easy. So the BI4ALL proposition is to do everything inside a dimensional model: ODS, archive, and virtualize the data marts. This is a huge change. If you stop and think about this for a second, there are 1, 2, 3 different modeling techniques in this diagram, which means these are incompatible, fundamentally incompatible, because they're different modeling techniques. Whereas this says same modeling technique in different areas, meaning they are compatible, meaning that when the hardware goes fast enough, and TwinFin Netezza might be this, these things can all cohabit, and there's no need to have separate physical databases and separate physical machines for the ODS and the archive data warehouse. I said in 2003 that it seemed to be in about 10 years' time we should have machines fast enough to cohabit the ODS and the data warehouse. And we're not far off that if TwinFin is the machine it's supposed to be. So the BI4ALL proposition says we increase query performance because attributes are broken out to type 1 dimensions and joined directly to fact tables. All joins are through integer keys. There are very few type 2 dimensions within BI4ALL, and because there are few type 2 dimensions, even databases like Oracle and DB2 can effectively process those data models. The same data model can support the ODS, the data, and the data warehouse query patterns. And you do not have to build data marts. You can answer all your queries directly from the ODS or data warehouse, and this results in approximately a 40% reduction in the ETL coding and maintenance cost, which does not include the extra 50% reduction we get for using CTL. You can avoid the hardware and software cost for data marts. Now, all data, remember, in the time variance stability analysis model, that data is not readily available for query. You have to put views over the top, or as Bill said, you have to get a COBOL programmer to go and ask it a question. Whereas in the BI4ALL proposition, all data is readily available to end-user tools, such as business objects or Oracle query and all these things, and all data is in a star schema, even archival data. Now, as part of this public presentation, we're not going to explain how archival data manages to be delivered via star schemas. Okay, that's something that we keep to ourselves, and we only tell the most serious of prospects about. Now, that's already 28 minutes, so you may say, enough of the background, show me something new. Terminology: everybody should understand a fact table stores facts such as revenue, profit, costs, price, quantity, and interest rates. We use the term major dimension to refer to the dimension table, and so typical things we would call a major dimension: time, product, customer. And we use the term minor dimension to describe a field, which is generally descriptive of a descriptive character field about some aspect of an object that is involved in the business. So for time, we have day, week, month, quarter, year. For product, we would have things like name, color, size, weight, height. For customer, we have name, birth date, age, sex, marital status, life stage, things like that. In terms of tables, we have an association type 1 table that we will talk about, which associates two or more tables to each other. An association type 2 table that provides time variance support within the star schema that we won't talk about. Type 1 dimension tables, which you should know about, and type 2 dimension tables, which you should know about. Terminology, fact tables, minor dimensions, major dimensions, integer keys spread around. Naming standards in BI4ALL. T as the first letter denotes a table. TD is a table and a dimension table. TF is a table and a fact table. Views are prefixed with the letter V. VM means dimension table and VF means fact table. So where you see VM, it means dimension, VF means fact. And views are placed over tables. There is no direct access to tables within the BI4ALL data models. So let's talk about some specific data models, specific tables within the data model. Month is a very standard type 1 dimension table, and so the view that gets created for month looks like this. So notice that the table is called TD00005, which is a meaningless name, and the view is called VM month. Therefore, the primary key in the select brings out PK VM month. So PK, the naming pattern is the name of the view is prefixed with PK to define primary key. Where you see PK in BI4ALL, you know you're looking at a primary key. The date is aliased as the first day of the month, and then these are the month fields. We have a thing called level column, which tells us the level at which this information is in this dimension table. And we have the OR clause to expose a 0 row, because when a lookup fails, we put a 0 in the fact table to indicate that the lookup failed. And that must join to a row in the dimension table so that no data is lost through lossy joins. You have the opportunity to rename fields, such as aliasing them PKTD00005 to PKVM month. This is the simplest of tables. Demographics is also a type 1 dimension table, but it has a little bit more information in it. So for example, you see the table name is TD00001. That is a meaningless table name. You see the level column is set to detail. You see the table number is set to 101. And you see that the primary key is tested with an OR to 0. You see that underneath the view, the fields have meaningless names. Now integer 01, money 01, money 02, integer 02, integer 03, these things are fairly self-evident as to what they are. Char 01 for gender is fairly self-evident as to what it is. So a demographics table, or a type 1 dimension table, exposes all the demographics for all the types of parties. It contains bands, so income low, income high, and the income band is there. It shows the dimension table number 101, and it shows the renaming of meaningless fields to meaningful fields. So here are the meaningless fields, which tell you the data type of the field that's being presented, and here are the meaningful fields, giving you the things that you would use within a query. Now, a type 2 dimension table. A typical type 2 dimension table is something like product. So product goes into a table called TD0200, and that is the meaningless name. And so PKTD0200 is exposed as PKVM product. Now you will note there's a date from, date to, and a current flag. So down the end we see date from, date to, current flag for the product. This is telling you that this is a type 2 dimension table. We have a level column of detail, and we have a dim table number of 146 for this product table. You can see things like, which are very obvious about products. You have SKU number, barcode number, product names, subgroup, group, category, etc. Product line, the size, the color, what's its shelf life in days, what's its allocated ABC accounting cost. Does it need a return inspection when it's returned? Is it returnable or does it need an inspection? Is this a sellable component, or is it actually just a component that's not sellable? All these kinds of things get stored about products. Company reporting structure is another type 2 dimension. So the company reporting structure goes from one date to another date with a current flag telling you what's current. And it does things like the parent company, the organization, region, channel, etc., right down to the individual person. And I've even seen autoteller descriptions or autoteller IDs on company reporting structure in banks. So because the company structure changes all the time, a type 2 dimension is used to maintain reporting structures for the reporting area. A separate recursive hierarchy is kept to maintain the actual hierarchies, so that cases where missing levels of the hierarchies occur, that can be more easily managed. So for example, you may not have a team category, or you may not have region names or channel types within your particular company. So they're included in this dimension table, but they would not be included inside the recursive hierarchy. So now we have something like parties, and a party is a human being, like a person, or a company, or a household. They're the three types of standard parties that we deal with. So a party has some specific fields about it which you would all be familiar with. You have a prefix, a first name, second name, third name, concatenated name, informal salutation, written salutation, address to name, how you address the person, their email addresses, web addresses, text numbers, phone numbers, and then things like the system assigned rating and the human being assigned rating. Are they a customer, employee, reseller, or a sales rep? Can we send them paper mail? Can we send them email? All these kinds of things are put on persons. Now for organization, you'll have things like number of employees, gross revenue, gross profit, net profit, organization keys, switchboard numbers. These are all things that any data warehouse architect worth his salt who's created a record to store party information in has created one of these. Now note, party is a type 1 dimension, although it may be implemented as type 2. The types of parties that there are, this is the current list just out of the box for BI4ALL. A person, a household, organization, a sales rep, a person who's a customer, an organization who's a customer, a household who's a customer, or a vendor, as well as one for just exposing all customers depending on what they are. We have other types of tables, such as indicator tables, which just carry a set of flags. So for an account, you might have is credit allowed, what's the payment, is there an interest penalty flag, is there a monthly fee or an annual fee. So these kind of indicator tables, sets of flags, yes or no, which tell you something about the thing that they're an indicator table about. So a good example is for address indicators for insurance. When you have an address, you want to know, is it a weather hazard? Could it be flood? Could it be storm? Could it be cyclone? Could it be hurricane? Could it be earthquake? Could it be subject to drought or anything else like that? Product cross-holdings. If you want to know what people own, what combinations of products, then if you have a relatively small number of products like telephone companies do, you may do a product cross-holding indicator, where this will be a set of yes or no flags which tells you, does the customer hold this product in a current contract? And then you can do things like analyze the customer base for customers that hold one product but not another product. So call waiting but without call line identification. Three-way calling but not three-way calling but not call line identification, or something else like that, or not calling circle, and these kinds of things. So a lot of the telephone companies have options, and these options are sold in bundles, and you want to figure out which people might benefit from taking the bundle. Now let's talk about associating parties. So a party can be associated for a reason, in a role, for a period, for a specified amount. So for example, one company can own a portion of another company for a period, and then that portion of ownership of that company can change, and that would be reflected by a change in a new row in the party-to-party association. Okay, so you can see in the party-to-party association you have the primary key, you have a string key, you have party 1 and party 2, you have the association code and the role with the from date and to date, with the dates actually put on there redundantly, and you have a current flag, and then with the description of the association code and role also redundantly, and the association amount, we've put 2 amounts on there, and then party types to tell us the actual types of the parties which are being associated. So this deceptively simple table is what is used to associate parties together. Now parties are associated to addresses, and the address, we say that the address exists independently of the party, and the party is associated to the address for a period of time for a reason. So for example, we may have residential addresses, we may have business addresses, we may have our holiday home if we've been lucky enough to be able to afford to buy one. And some simple fact tables. We'll just show you some simple fact tables so that you can gain an understanding of them. One of the typical fact tables that you would have is an account close transaction. So if an account closes, you would want to record lots of information about that account closure. And so a fact table, you see it has PKVF account close transaction. So we actually put unique keys on the front of all our fact tables, and that's something that we talk a little bit about and provides us with a lot of benefit for doing. The account transaction date, minute, the account, the campaign, contact method, the product that was being used, and the customer, and the demographics, etc. If there's a card associated with it, and a card type, and a map reference, and geography. So there's a lot of information linked to the fact table as a set of keys. Now note that the company reporting structure is on there. The company reporting structure is everywhere. And note that these 3 keys, which are links to fact tables, to the account dimensions association, customer dimensions association, and campaign dimension association tables, are put on all fact tables, or virtually all fact tables. Now this slide says more on these later, not in this presentation. If you are interested in what you see, then we can explain more on that later. You will see we have a fact table number, and we have a fact table TF0101. So the account close transaction goes in the TF0101 table. Another very standard table, which you will all be familiar with, is invoice lines. So every organization virtually produces invoice lines. As Ralph said, the invoice line is the single best piece of information in a company, and it is the first thing that anybody should start with when building a data warehouse. So PKVF invoice line with an invoice date and an account and the account dimensions, the product, the customer, the currency, the geography, the geocoded map reference, the order date for the invoice, the company reporting structure, the account status, etc. We have the invoice number as a string, the invoice number as a number, the line number of the invoice, the number of units, the base amount, the extended amount, the tax amounts, the unit amounts and the extended amounts, and then descriptions of what's on it, the scheduled delivery date, the scheduled payment date, and the number of lines, which is set to 1 for summarization. So that is a very simple fact table, invoice line. Now what we're going to do is, I suggest you actually, it's been 46 minutes in this demonstration already, and we're now going to demonstrate to you the data models. So I would suggest you take a short break because the next piece is going to be fairly detailed because it's the demonstration of the data models. Now the first part of demonstrating the data models is to show you how tables are defined. Now this is how tables are defined in BI4ALL. There is a Create Tables tab in a CTL workbook, and you can tell it's a table. It has table name, column name, deploy data type for documentation, deploy null clause, documentation null clause. So just to explain this, we have developed a mechanism whereby we create tables, one of which can be deployed to the deployment database and one of which can be deployed to a documentation database. So if you have Netezza, for example, and you want to create tables on Netezza, you create one set of tables for Netezza, but if you want to document it on SQL Server, you create another set of tables for SQL Server, and you document onto SQL Server. If I zoom in on table name, you'll see the different table names here, and rather than go and look at it, you can take my word for it that this actually does create table statements at the end of the day. So here's table 2, here's table 3, etc. And we will go and see those tables live in the database in just a minute. The next thing to tell you about briefly is joins. So data model joins are defined inside this workbook as well, and this is the left table, left column, right table, right column, with the join type and cardinality. And this can be used to directly update business objects universes, and it can also be used to create constraints SQL against SQL Server. And just to prove that we've done this, this is line 5267, and that is indeed how many joins there are in the current version of the BI4ALL data models. And yes, they do actually all get generated and all get applied to the database. So I just wanted to show you that when you build BI4ALL data models, you do put the RI constraints, or the joins, into another CTL workbook. And now for the data models themselves. The way the data models are delivered to the customer is via an Excel workbook. And this Excel workbook defines the number of languages. The data models out of the box only come in one language. If you wish to translate them into other languages such as German, French, Spanish, you are free to do so. We don't speak those languages, so we haven't converted them. And when you have multiple languages, it puts the information into different target directories. So how do you define a view? Well, there is a VDSD, so view descriptions, short descriptions. So each view has a submodel, has a view number, and a short description about it. That description can come in many languages. So this short description gets loaded into the dictionary so that you can do queries on the tables and retrieve the short descriptions. I'm just going to scroll down a bit. The next piece is long descriptions, where you have the table name plus a long description can be entered in here. So there is both short and long descriptions for each and every table. Now we get down to the view column definition. Now the way that data models are defined in BI4ALL is you have a table name, these are the meaningless tables, you have a column name, the meaningless column names, you have a view owner, then you have a view name, a view column name, you have short and long help text, and then you have short and long help text in as many languages, or then you have view name, column name in as many languages as you like, short and long help text in as many languages as you like, up to and including 10. So the O1 language is English, and you have 9 more languages that you can use. Now if we were to drill on this one, we can see that there's a rather large number of tables in here. The number is actually 847. So if we scroll on VF account close transaction, we see the table name, the column name, the VF account close transaction, which you saw documented, and column 1. So you saw these keys in the create view statement, and then there is help text for each and every field inside the 28,000 fields in the dimensional model. Okay, so let's pick some other view. We'll pick VM party. VM party. So this is the table name, TDO100. These are the meaningless column names. This is the view, VM party. And here we see things like first name, second name, address to name, marital status, gender, etc. All the things that you would expect to see on a party record. So this is the way the data model is delivered to you, the customer. Now let's go and have a look at it in SQL Server. So here we are, SQL Server Management Studio, BI4ALL 3000, and if I click on tables, we'll notice that there's a lot of CTL tables. Now those CTL tables are the control tables and data dictionary for our ETL product called CTL. And the TD tables, just 15 or 20 TD tables at the end, which contain a whole bunch of views over the top. So if I pick TD 0001, and say select star from TD 0001 and execute, I will actually get some data back. Now over on the right hand side here, no, hang on a tick, table number, this table number 103, 107, this tells me what dimension table that particular row of data should be looked at, and it changes. So we have all these fields, so many of them spread out. So table number 118, 123, 126, 125. So all these table numbers are different, and they are exposing different views out of that table. So you see there's not many tables here, and there are certainly no tables called VF or VM. Now when we go to Views and click on Object Explorer, we'll see there are 848 items, so 848 views. And here is Account Close Transaction. We can also open it up here. So Account Close Transaction, we can see that it's a view because it's in the database views, and obviously in a view PK is not actually a primary key. Okay, it is and it's an integer, not null, and account date is DKVM account date is integer, not null. So you can see the data types, and you can see this information following on. So if we go back to our spreadsheet, and go back to VF account close, we can see the correlation between this column name and this column name in the spreadsheet has been put into the database. Okay, and if we were to click on this and say script view as create to new query editor window, we would see create view, select from these things these columns. So you can see that the view is over this table and the aliased fields are presented. Okay, and like I said, there's 848 of these, and we can go into detail in a more detailed confidential discussion. We can go into detail as to what all these tables are and what they all mean. Yeah, but what we want you to get at the moment is, or understand at the moment, is that there are 848 views with 28,000 fields in them in this data model, covering a very wide variety of things that you would want to cover. If we were to sit down and list them, this would take us quite a long time. Now there's another database called BI4ALL003. The D means documentation. If we click on the views in this database, there aren't any. Okay, but if we were to click on tables, we will find table names that are suspiciously like our view names in the database above. So here's account close, account dims, transactions, account measures. Yeah. Account transaction close, dims, account measures, account plan, account transaction. So those views are instantiated as tables in the documentation database. If I click on this view, I see I have an account close transaction, I have a primary key for account close transaction, and you can see by the color of that key that that is a primary key. So inside SQL Server, this table has been allocated a primary key, and that is done by CTL by reading the ETL spreadsheet. You can also see all the RI constraints that have been put into place. So these RI constraints actually tell us the constraint, the dimension table that this table is linked to as a constraint. And you can see that these are actually data fields now. So what we've done is we've taken the view that's in the deployment table, which can't have a primary key and which can't have constraints applied to it, because you don't apply constraints in data warehouses anyway, and we've created a documentation database which represents the view one for one as a table, applies the primary key constraints, and then applies the RI constraints. So what is this useful for? this is useful for you to import into data modeling tools if that's what you want to do, being able to see your data model in a data modeling tool. So this documentation database is useful for data modeling tools. Now if we just want to have a look at some of the fact tables that are in here, we see things like plan, measures, plan and transaction. Now virtually all data modelers will be familiar with the idea of a transaction fact table and the idea of a measures fact table, which takes transactions up and creates measures on a periodic basis. Not so many will know about plan tables. So a plan table is if a customer decides that they want to plan a piece of the business, then they create a plan table to store the plans, which are usually stored in Excel spreadsheets or some kind of planning package. So an account plan table would tell you how many new accounts or closed accounts or open accounts were expected within this planning period. So this is a very good example of a plan table. And you have things like accounts adjustment measures, adjustment transactions, accounts payable, invoice headers, lines and measures and transactions, contract dimensions, contract transactions, contact transactions, customer measures, delivery transactions, fraud transactions, file transfer transactions, invoice line measures, invoice transactions. Then we're getting into the media model, F media, order header, order line, order measures, parties, and then RET is retail. Our segment is our segmentation engine, solicitation and solicitation measures, and there should be response. Response measures, response transactions, okay, for solicitation and responses. Tel is for telco, and we have a lot of telco tables. Web is for web-based businesses, and we have a few tables in there. And then we have all the dimension tables which are linked to all these fact tables. There's quite an endless lot of them, so we do have to go through them in more detail in a separate presentation. So you have behavior scores, blacklist, building types, campaigns, contact dates, methods, all these sorts of things. So every single one of these tables is defined to have its primary key, its fields, and the description of the field is also stored in the data dictionary, and there are reports in the data dictionary over the top. Now we have this concept called everything is linked to everything, and so we don't actually typically draw diagrams of these data models. What we say is if two tables are supposed to be joined together, then they will be joined together, and you don't need to worry about that. And if they're not joined together as they're supposed to be, or there's not a navigation path between them as there is supposed to be, then we can create one very quickly. So I just wanted to show you that these data models are real, they do exist, they are created in SQL Server, all 847 tables of it, all 28,000 fields of it. Naturally, to actually go through it and evaluate it, to understand the actual coverage of it and to see what's there and what's not there is a longer exercise. But what we are saying now in our offering is we are using this as a base. We will build your data model for you using this as a base, and instead of giving you the entire BI4ALL data model back, we will give you back just the data model that you need to run your business. So you never need to learn the BI4ALL data model, you just learn the piece that you get as a result of the development project. And we think that's going to be a more feasible way to go about it than to try and explain to customers the massive number of tables and fields and columns, etc. within the BI4ALL data model. But we do want you to see it such that those of you who have an interest in it can see at least this is what is there, and you can say, okay, well, I'm willing to spend the half a day or day that it's going to take to go through this data model with these guys. Now, because we've got such a sophisticated data model, and we know that it works, and it's been implemented, or prior versions have been implemented in many, many places, and we're now bringing out this new version, we know that the process of BI4ALL data modeling has changed dramatically over what we used to do in years gone past. So we're going to give you in this presentation a brief taste of the process of BI4ALL data modeling. This is very different to what people are used to. The reason that it's different is associations dramatically change the process of data modeling, and associations, the type 2 associations, make the data modeler's life much easier and eliminates some significant problems by design. So these things dramatically enhance our productivity and dramatically reduce our development times for our data models. So how do you go about this? When you do BI4ALL dimensional modeling, the first thing you do is you identify the dimensional data, and you define and design the dimension tables. You do not worry about what fact tables it will be linked to or anything else like that, and you attempt to define unique discrete values within dimension tables only. You almost never define a type 2 dimension table. If there are large combinations of values, we break the input data into more and smaller dimension tables to keep the number of rows in the dimension tables relatively low. So we create many more type 1 dimension tables and put all combinations of the fields, the valid values for those dimension tables, into those dimension tables. We decide which dimension tables then need to be type 2, and usually there are very few of those. Such examples are current company reporting structure, product, and geography. Once we've done that, we then sit down and we determine what the real key is in the source data, and we might use things like our profiling tools to find that out, as well as just our experience and our knowledge of the operational systems. And once we've done all that, we map it to a BI4ALL table or define it to a new table. So we look at the dimensional data in our mapping spreadsheet on the left-hand side first, and we figure out what we want as a dimension. And once we've figured out what we want as a dimension, then we look in the BI4ALL data model to see if there's something similar that we can reuse, or we create a new table. So most of that work is looking left at the source system, not looking right at the target table. So for fact table modeling, we identify all the transactions, and basically we say if it's a transaction, it's going into the data warehouse as a transaction table. And because we can do the mappings so cheaply, we don't need to worry about the time and effort spent doing that. So identify transactions and take them into the table, and also the key measures data. So we will identify those things that we think are key measures that need to be put into the data warehouse. We then define and design those fact tables, and initially we only worry about linking the dimensions that are unique to the fact row and dimensions to the fact row, and dimensions obviously required for performance. We do not think about linking low-use dimensions to fact tables. Now, the problem we have had over all these years, and which still many other people do have, is that if you don't link the dimension table to the fact table, and at some future point in time you realize that you made this mistake and that you do indeed need to link some dimension table to a fact table, typically you need to change your ETL processing to do that. You need to add a key to the fact table and alter your ETL processing. And this is why so many data warehouse architects have grey hair, because the trade-off between adding lots and lots more dimensions and the performance and and ETL processing that is required has been a very difficult trade-off to make over many, many years. And so one of the new innovations of BI4ALL is to do away with that trade-off by design. So we link fact tables through association tables to other dimension tables so that we can get to the dimension table in one hop, and we don't need to go grey worrying about what dimension table keys we need to add to fact tables. We guarantee that we can get to nearly all dimension tables regardless of whether they are directly connected to the fact table. We refer to this as everything is linked to everything, or the other reference we have is we say we build a mesh, and the idea of a mesh is that a mesh is highly connected to everything else. So if you have a mesh of something, like a net or something, there are many, many, many connections in a mesh. So we talk about building the mesh into the database to join things together. And it's not unusual for us to build 800 or so connections between tables in a decent sized data warehouse. So then we put the relevant association keys onto fact tables like party and account and assume if it should be linked, it will be linked. We then add extra keys for performance as reports are designed and as analysis requirements become more clear. When we do all that, we map it to a BI4ALL fact table if one exists, or we create a new table into the BI4ALL model. So when we come to modeling history, we identify the areas where you want to retain history, and entity and accounts are already defined, and you might add end of month outstanding balances or daily outstanding balances or things like that. You decide how you're going to retain that history. Will I put it into a type 2 dimension table? Will I develop a new association table? Or will I even develop an event fact table with a current previous amounts? This is quite typical in banking transactions with before-after withdrawal balances. So these are the kind of decisions to be made about history modeling. Now, BI4ALL modeling is far faster and easier than the other current methods of designing data models. If you are using a data modeling tool, we know that we can design and develop and implement models at around 5 times faster than people can do this using a data modeling tool, even if they have a pre-established model in that data modeling tool. And the reason that we can say that is many of the people associated with BI4ALL did spend time implementing the prior generation called Sybase IWS and using Sybase Power Designer as the tool of choice to update Sybase IWS. I myself did that for nearly 5 years, and it is an exercise in click yourself to death. So these ER tools are diagramming tools for databases. They're all very nice and they do draw you nice diagrams, and we use one ourselves. However, they do slow you down and they don't support presenting the data model in multiple languages, and they don't support this ability to create one set of definitions as views, which is your real data model, and then translate those views immediately into and simply into tables with the primary key constraints and the RI constraints, and then diagram that. So what we are proposing to customers is we provide the database which has the RI constraints, primary keys, etc. defined. You re-engineer that into whatever ER tool you like, and then every time the data model is changed, point your ER tool at the documentation database and get the tool to find out what's different about the database now and update its diagrams based on what's different. BI4ALL modeling produces faster and cheaper data warehouse, both to design and to run, and has no loss of functionality over anything else you might do. Now, in saying that, I've recently been talking with Dan Lindstedt about Data Vault and things like that, Now, in order to store the historical information within a dimensional model, there are some compromises that are made within BI4ALL, and those compromises are primarily about redundantly storing information. Now, with the price of disk and processing, redundantly storing information, I would argue, is not a significantly high cost to pay for being able to have just one single data modeling technique. However, having said that, I've known Dan for a long time, and I've only just really researched Data Vault to see what it's all about. And if you want an archival data model which stores everything, then Data Vault is a pretty good idea. I see that Data Vault, because it is of its nature, you're not going to build star schema queries on top of a Data Vault in the majority of cases, and therefore there is still a home for some kind of star schema model even in large companies that build Data Vaults. Now let's just re-summarize this because it's so important. In 1996, a colleague and I sat down and put our heads together, and we combined the best ideas of Bill Edmond and Ralph Kimball, and we came up with an idea where we would have third normal form ODSs, we would have the current detail and archival store in third normal form plus time variant and stability analysis, and then we would put the lightly summarized and highly summarized data in star schemas, and sometimes cube type products like Holos, which was very popular in the late 90s. And this was a very good idea. It gave us the most comprehensive business intelligence architecture in terms of data. It also gave us the most expensive architecture in terms of data. The BI4ALL proposition is to turn the data into a star schema even by the time it goes into ODS, if you can afford the ETL processing that does that. Now that ETL is pushed into SQL inside the database, I argue that this is readily affordable. In the structured for the enterprise data warehouse, which is non-application specific, and the older detail, we are now saying that that can be done purely as a star schema, and the older detail can be done purely as a star schema, and you can have virtual lightly summarized stars or highly summarized stars because that information is also sitting in here. Now there are still some cube products out there, airspace being a good example, so data may be drawn from here and put into some cube type products. But this is the new proposition. The new proposition is just one data modeling technique that will serve everything, and by doing that you simplify the ETL apart from the initial piece of ETL, and you reduce the number of data models and physical instantiations of databases inside the overall architecture. So, next steps. If you like what you have seen in this roughly 1 hour and 15-minute presentation, you would like to see BI4ALL in more detail, what we did was we flashed 847 tables in front of you. Obviously you didn't read those tables. You've got a general idea of the subject area of those tables. But if what you see is of interest to you, and you are thinking, you know, I could build my own data model, or I could buy this data model, or have these guys build a data model for me based on this data model, this sounds like a good idea rather than reinventing the wheel. There are very few data model vendors out there, IBM, Teradata and HP being the top three, with HP having theirs mostly in banking. Given that the majors are out there selling their data models for telephone number prices, you are welcome to go and look at what they've got. Welcome to ask them questions about it. We would, if you are interested in what we have to offer, we would arrange for a detailed live demonstration, typically over the web, of the BI4ALL models and that demonstration would be considered confidential because we would spend between 4 and 8 hours depending on how many people you wanted in the discussion, depending on what it is you wanted to see, and we would go through in great detail everything that's in the data model. For very large clients who are considering significant projects, we've typically gone to the client for a day, put everything onto a projector and everything up for discussion such that people can vote on it over the following week or so, and then decide for themselves whether they want to go with this data model or some other data model. One of the issues we face with that is the number of customers who've asked for that who have been kicking tires, and so we'll enter into discussions with prospective clients about how to discourage tire kickers for those kinds of things. So if you are interested in reviewing in more detail the models to determine the fitness for purpose, by all means contact us at Instant Business Intelligence, and we will sort out a way and means of bringing you this information such that you can more effectively evaluate it and make a decision for your organization. So in summary, we went through some names you should know, the key issues in modeling, the traditional design mechanisms, what became best practice in 1996 and how we are better than that now. And then I just took you through some terminology, some naming standards about tables, and showed you the representations of some of the tables in BI4ALL. And then we had a fairly swift run through the actual models to show you that there are plan, transaction, measures, tables, fact tables, and type 1, type 2 dimension tables. I pointed out that there's 847 of them now. There's 28,000 fields. We have people who are references who will tell you these are very good models and references that are impeccable. And so it's really up to you to look at that and say, well, this is very interesting. Do I want to investigate the proposed use of these data models, or do I want to not investigate the proposed use of these data models, and come back to us and let us know what it is that you're thinking. Obviously, as a small consulting firm, a small software firm who's brought these data models to market, we're interested only in talking to people who are actually interested in doing a project. We are less keen and enthusiastic to talk to people who want to be educated. Now, we would ask for your honesty in that. Please call us if you're interested. If you want dimensional modeling education, please call my good friend Ralph Kimball and go and enroll in his classes and read his books, because Ralph makes his living out of educating people about how to build dimensional models. We don't want to be providing free education, where Ralph provides a very good service for all who come to his classes. Having said that, we'd like to say thank you very much. Thank you very much for your time. We appreciate your time and attention for such a long presentation on such a complex issue and complex product. If you are interested, we would be delighted in hearing from you and delighted in explaining to you BI4ALL in more detail. Thank you very much for listening.